Good morning.
Sure.
So let us proceed with the lecture 15. So just to recall the things that we have done yesterday. Yesterday we have learned about the properties of Laplace transform. Okay, starting from the introduction of Laplace. Then we have learned about the inverse of Laplace transform. We did learn about the partial fraction, review of partial fraction. Then we have learned also we have understand about the poles and zeros of Laplace transform, and afterwards we have learned about the properties of Laplace transform. Yeah, so a few properties have been learned yesterday, and we did few examples in order for us to to ensure that all of you understand the properties of the Laplace transform. Yeah. Okay, so let us proceed with this lecture 15, which is covering the topics of application of Laplace transform. So if you can recall, yesterday I did mention that Laplace transform has been used or is widely used in solving the electrical circuit analysis problem, which involve the existence of R, L, and C. Okay, so we have learned that when we have R, L, and C in our circuit, basically they should involve an equations in time domain which has the integration and differential terms, in our time domain equations. So the purpose of having Laplace transform is that we can transform these time domain equations into a frequency domain, okay, in which we have simplified the equations into algebraic form, okay, and the solutions in algebraic form should be easier, okay. So we solve it in frequency domain, and afterwards, in order to find the actual values in time domain, what we did is we're going to transform it or to inverse it back to time domain. Okay, so this is what we have learned yesterday. Yeah, so this is what we're going to learn in lecture 15, the actual application of Laplace transform. So two topics will be covered. The first one will be the Laplace transform for passive devices. Okay, so this involves a Laplace transform for the R resistor, for the L inductor, and for the capacitor C. Okay, so we need to understand this first before we can proceed with the circuit analysis, which will be the second topics in lecture 15. Yeah. Okay. All right. So let us proceed with this first slide here, which is on the Laplace transform for the resistor. Okay, so what we have here in this slide is that we are having the equation in time domain for the resistor here. Okay, we have the V, okay, equals to IR. Okay, this is in time domain. Okay, this is very familiar equation, the Ohm's law. So we need to transform this into the Laplace. Okay, so this is what we're going to have, where we have the Vs. Yeah, the Vt is transformed to the Vs. The R remains as R, and the IRT or the recurrent resistor is now transformed into the IRS, or just simply we just write as IS, it's good enough then. Okay, so for our case here, for Laplace transform, your impedance Z is R, so that should be the impedance of the resistor in Laplace transform. So this is your circuit transformation. So what we have here is your circuit in time domain. So we have the resistor R, the VR is the voltage drop across the resistor, and this is the current flowing through the resistor. So when this particular circuit transform into frequency domain or the S domain, okay, so we're going to have the R still there, okay, the voltage drop across the resistor is known to be the Vs, okay, or the VRS, and there should be a current of Is flowing through the resistor. So these are the things that need to be understood. So the first thing is that the equations of the components, from the time domain to frequency domain to S domain is written to be in this form. Okay, and the circuit transformation is given down here. So that is the circuit transformation, which will need to be used yeah, when we are going to solve the problems of circuit analysis later on, yeah, in the next slides. Okay, so that's done with the resistor. Hopefully you understand this clearly. So in case if you have any question, you can just ask, yeah, during the lectures. Okay, the second one is about the inductors, transformation of the inductors. Okay, so this is the very popular equations for the inductor V equals to L di dt. Okay, I think all of us have seen these equations before. Right, so what we're going to do now is that we're going to transform into the Laplace, into the S domain. So this will involve the properties that we have learned yesterday. Yeah, if you can recall yesterday when we have differentiation properties, if ft gives us the fs. So if we have dft over the dt, which is a first order differentiation, is supposed to be s of fs minus f0. Yeah, okay, this is the equation yesterday. So this what we're going to use in these equations. Yeah, so the di over dt is now returned to be in this particular form. Okay, so we have s of is minus I0 negative. Okay, this is a steady state value. Okay, steady state value, right? The VLT is written to be the VLS. Okay, right? So that should be the equation that give us the voltage drop across the inductor in the S domain. Yeah. So basically from this equation, we can say that the impedance in the S domain, yeah, the ZLS is SL. Yeah, so SL should be the impedance in the Laplace on the S domain. Yeah. Okay, so this is the equation. And for the circuit transformation, so what we have here is the circuit in time domain. So in frequency domain or in the S domain, this is what we're going to have, okay, which is based on the equations here, yeah. Okay, this is based on the equations. So the VLS is the voltage drop, okay, and the voltage drop consists of two components. The first one is a voltage drop across the inductor itself, which is the SL, multiplied with the ILS, okay. And the second one is the voltage source given by this component here, which is the Li0 negative. Yeah. Okay, Li0 negative will be the the voltage source which is produced from the transformation. So we can see that from this diagram, in the S domain or in the frequency domain, the inductor is represented by this component. Yeah, so means that when we want to transform the circuit from time domain to frequency domain, means that a transformation of the inductor. So for the inductor case, you have to transform the inductor into this form, where the inductor is written to be SL, okay, and that involve the voltage drop of Li0 negative, okay. So that should be your transformation of the inductor component. Okay then, yeah, all right. So let us proceed for the next slide. Okay, this is for another case. Okay, for the previous case here, this transformation will be very useful when we are dealing with the application of Kirchhoff voltage law, KVL. Okay, will be very useful for that application for KVL. But in case if you are using the KCL, Kirchhoff current law, in solving your problems, so that this should be the alternative equation that can be applied or can be used. Okay, in which these equations here is basically obtained from the previous equations. Yeah, so we need to write the ILS in terms of the VLS. So if we can write here, so let's say we have the VLS equals to SL of ILS minus LI L0 negative. So in terms of the current, so ILS should be equals to 1 over SL of the VLS plus IL0 negative divided by S. Okay, so this should be the case, okay, in which we want to write the voltage, sorry, the current of the inductor in terms of the voltage. So this is the equation that has been shown in this slide. Yeah, in this third slide here. Okay, so the same things apply in which the impedance still SL. Yeah, we just change the orientation. Yeah, previously is the current in terms of the voltage, but here is the voltage in terms of the current. Yeah. Right. So as I mentioned, the equation here will be very useful when we are dealing with the Kirchhoff current law. Okay, in which if this is your component, the inductor. Okay, the circuit or the component, the inductor component can be written in this particular form. Okay, which is based on these equations here. So the current, the ILS, is equals to two branches. The first one is your voltage drop. Okay, the current, sorry, the current flow, VL over the SL, about current flow through this branch. And the second one is a current source, which is IL zero negative divided by S. Okay, so we have two branches of current. So the ILS consists of two branches of current. The first one is the current flowing through the inductor, yeah, which is the VL over the SL. The second one is the current source given by IL zero negative divided by S. Okay, so that is based on the equations here. Yeah. So these are the transformation for the inductor from the time domain to the S domain. So I repeat again, for this particular slide, it is the inductor's current is written in terms of the voltage, right? And that should be the circuit transformation in the S domain. Okay, so you have to remember these circuits diagram in the S domain. So there's nothing much. We just based on the equations here. Yeah, we just based on this equation. Okay, this equation is very important. So every time when we want to draw, when to sketch the inductor component, you have to be based on these equations. Yeah, and the same things apply. This is for the case of the voltage inductor in the terms of inductor's current. Okay, and this is very useful if we are solving the problems using the Kirchhoff current law. Okay, in which if you base on the equations here, the inductor current consists of two branches. Yeah, the first one is the current through the resistor, sorry, through the inductor, the VL over the SL. Okay, and the second is the current source, which is IL zero negative divided by S. Okay, yeah, so far so good. Is it understood? Sorry, yeah. So so far so good, yeah. All right, good. Thank you very much for the response. Yeah. Okay. So let us proceed with the next component, which is a capacitor. Okay. So this is a capacitor equation. So we have seen these capacitor equations before, right? Which is I equal to C dV over dt. Okay. So what we're going to do now is that we're going to transform this into the S domain. So this is what happened. Okay. So initially, if we transform, the equation can be written as I C of S shall be equals to C. So that will be written as S of V, C of S minus V C zero negative. Okay, so don't worry about negative sign. Yeah? This negative sign means we are dealing with the values of the initial voltage, yeah, which is having in stable state, yeah, the stable condition for a long time. Yeah, so don't worry about this zero negative. Okay, so from these equations, because we want to write the capacitor's current, sorry, we want to write the voltage, capacitor's voltage in terms of the capacitor's current. So we need to write it in terms of this. Okay, so we need to rearrange the equation here, right? So when we arrange it, supposedly we're going to have the equations down here. Yeah, the VCS shall be equals to 1 over SC of ICS plus VC zero negative divided by S. Okay then. Okay, so that should be the equation in the S domain. And from here, evidently it shows that your impedance for the capacitor should be equals to 1 over SC. Yeah, 1 over SC should be the impedance. Yeah, 1 over SC. Okay, and this is your circuit's transformation, the diagram. In time domain, it will look like this. So in the S domain, according to this equation, the voltage drop across your capacitor will consist of two components. The first one is the voltage drop 1 over SC divided times the ICS, okay, given by this component, okay, 1 over SC multiplied with the ICS. And the second component of the voltage drop is the VC0 negative divided by S, which is a voltage source. Okay. Okay. One more thing to be remembered or to be reminded here. Please note that the sign of the voltage source is following the sign of the voltage drop. Yeah, because we have a net positive sign here. So the sign of this voltage source will be same as this positive, negative, and it's also positive and negative. Okay. As opposed to the inductor's case just now, okay, so we have a negative sign for the voltage source. Because why? Because if you base on the equations here, we have a negative sign for these component. Yeah, for this voltage source, the sign is negative. So this is why the orientation for this voltage source is against the direction of the voltage drop VLS. Okay, so please be notified on this. Yeah. Okay, so we have done with this. So hopefully you can differentiate. Yeah, what should be the transformation of both inductors and capacitors. Yeah, so far good. Okay, so these equations yeah, will be very useful when we are solving the circuit using the Kirchhoff voltage law, yeah, KVL. Right, and if we are dealing with the circuits that shall be solved using the Kirchhoff current law, so these should be the equations that shall be applied, in which again it is based on this equation, yeah, based on this equation in which we are now writing the current ICS in terms of the VCS, okay, in which if we write that, if we want to write the voltage in terms, or you want to write the current in terms of voltage, it should be written as I C of S, okay, and that should be equals to SC or VCS, okay, and we're going to have sorry, and that should be equals to plus, let me see here, so we're going to have this is minus, sorry, minus VC0 negative, sorry, 1 over SC, sorry, 1 over SC should be here, SC, so that should be C of VC0 negative, yeah? Okay, so that should be the equation that need to be used, yeah, if you want to write the current of the capacitor in terms of the voltage. So that is what we're going to have here. Yeah, this is the equations that I've been working on just now. Okay, so we have ICS using equals to C SC VCS minus CV0 negative. Okay, right. So from this equation, that should be the transformation of the circuit from time domain to this frequency domain, in which we can say that the capacitor's current is actually consists of two components or two branches. The first one is the current flowing through the capacitor, yeah, which is SC VCS, okay, SC the VCS, yeah, SC material VCS. And the second component is the current source, which is CV0 negative. So note that the direction of the current is from a negative to positive because of the sign of this current source. Okay, and we can compare this with the equation for the inductor before. Note that because of the positive sign for the inductor's component of the current, that's why the direction of the current here, current source is from positive to negative. Yeah. Okay, so that is the transformation for three components for the R. So for the R, nothing much difference. Yeah, we just change from T to S. That's all. So that no changes on the component itself, no changes on the impedance. But for the inductor, evidently it shows this is the changes that can be noted. Yeah, especially on the impedance value. Okay, which is the SL, and the existence of the voltage source if you are based on this equation, okay, based on this equation. All right, I hope that you please never try to never memorize the equation here, because you can always get it from this basic equation of the inductor. Yeah, simply we can get it from this equation, so never memorize this. So the same things apply if we are dealing with the these equations, yeah, when we are solving the problems using the Kirchhoff current law. Okay, and this will be your circuit transformation, right? And this is the equation for the capacitors, okay, both for Kirchhoff voltage law application and for the Kirchhoff current law application. And please, uh, uh, on the circuit transformation, yeah, circuit transformation, you need to know that this is the transformation that happens, yeah, in the capacitor component, yeah, from the time domain to a frequency domain. Okay. So any questions so far on this transformation of your passive components R, L, and C? No, yeah? Okay, if there's no questions, I think we can now proceed with the analysis of the circuit by using the information or the knowledge that we have learned from the previous understanding on the uh, frequency transformation or Laplace transformation of the R, inductor, L, and capacitor C. So those knowledge shall be now applied. Yeah. Okay. So as what we have learned previously in the circuit theory, yeah, circuit theory, you know that we can have two methods for the circuit analysis. Whether we can apply the loop analysis, number one, or you can use the loop node analysis. Yeah. So we have two methods there, loop or node analysis. So for the loop analysis, we need to use a KVL to solve it. Yeah, KVL. Okay, Kirchhoff voltage law. So this is the steps that need to be taken. In which first, if you have the R, L, and C components in your circuit, what you have to do is that you have to transform all of these components into its respective transformation. Yeah, in which for the resistor, we need to change it into impedance R. For the inductor, we need to change it into the impedance of SL, which is in series with the voltage source, yeah, which is according to the previous slides that we have learned. Okay, in terms of the capacitor, we need to substitute or to replace the capacitor in time domain with the impedance of 1 over SC value and in series with the voltage source also. Okay, so this is need to be based on this case, yeah. So for the case of the inductor, the voltage source is Li 0 negative with the sign of negative to positive, whereas for the capacitor, the voltage source is Vc 0 negative and the sign is positive and negative. So which is according to the direction or following the direction of the voltage drop of VCS. Yeah. This is what given by this equation, this statement here. So this is voltage source of Li 0 negative. And for the voltage source just now for the capacitor, it is Vc 0 negative over S. Yeah, Vc 0 negative divided by S. So this is what, this is the things that need to be understood. Okay, so accordingly, we need to transform the voltage source into the S domain. Okay, so we need to transform everything, need to transform the impedance, need to transform the inductor, need to transform the capacitor, and also need to transform the voltage source. Yeah. For instance, if your voltage source is, let's say, 2 volt, so the transformation from the time domain to the S domain shall be now returned to be 2 over S. Yeah, because we are taking that the 2 volt here is a constant value. Yeah, so we can also write the 2 volt as equals to 2 of UT. Okay, that's why the transformation of 2 volt is written to be 2 over S. So this is just an example, yeah? So it means that you need to transform everything, the components RLC, together with the voltage source, all of them need to be transformed into the S domain. Okay, right. Number two, step number two is to sketch. So you have all of these R and C and also the voltage source transformation. So that should be manifested in a transform diagram. Yeah, so you have to transform it, to sketch it into the diagram, the circuit. And afterwards, number three, then only you can apply the Kirchhoff voltage law, depending on the parameters that need to be obtained. Okay, so I think that most of you have been taught. I mean, you have a very good understanding on the circuit analysis before. So I'm hoping that you should face no problem, hopefully, in solving these related topics of Laplace transform application in the circuit analysis case, yeah, circuit analysis problem. Okay, good. So let's have a look at this example number 1, okay, in which we are having this particular example. Okay, so we are having the circuit here, which is having a voltage source of 3 ut. Then we have the inductor of 2 Henry, and we have the resistor of 4 ohm. Okay, so for this particular example, you need to find the value of IT, which is the current in the loop. Yeah, current in the loop. So need to find what should be the value of current in the loop, in which is given that the S current is closed for t bigger than 0, which means that initially the circuit or the switch here is open. The switch is open, and suddenly at t equals to 0, the switch is closed, and then only the current can flow through the circuit here. Okay, so based on that, we need to find out what should be the value of the current flowing in this particular loop, yeah, in which we assume that the initial current I0 negative is equals to 5 ampere, and this I0 negative is related to the inductor's initial value of current, yeah, IL, yeah. I0 negative equals to 5 ampere, because from these components, we only have the inductors as a passive component, and so the R. So for R, there is no such case of initial current or initial voltage, yeah. Right, so now we're going to do the transformation. So from what we have learned before, for the case of the inductor, you can refer back to the slides. Yeah, so the inductor, because we are now dealing with the Kirchhoff voltage law, so we need to transform the inductor into this particular form, where we have the inductor's impedance of SL, okay, and we have the voltage source of Li 0 negative, okay, and please bear in mind that the direction, the polarity of the voltage source is against, yeah, the direction of the voltage drop. So because your current is flowing in this direction, okay, so that's why your voltage source is having a direction against the direction of the current, so it's negative and positive polarity. Okay, so the SL, because your inductor is having 2 Henry, so you're going to have 2S as the impedance value, yeah, and for the voltage source, we have initial current is 5 ampere. So supposedly this voltage source value is equals to 10. Yeah? 5 times 2 should be equals to 10 volt. So basically that should be equals to 10 volt or 10 volt of voltage. Yeah? Right. So resistor remains as 4 ohm, and the voltage source of 3 ut is now transformed into 3 over S. Yeah? Okay, so we have successfully transformed your circuit. So this is in the S, in the T domain, time domain, and what we have here is the S domain. Okay, so we have transformed the circuit from time to frequency domain. Yeah, so in which we are transforming all the passive component R and L together with the voltage source in the S domains. Yeah. Okay, so this is what we're going to have, right? The circuit, and since you want to find the current flowing in your in your loop, okay, so the IT, the current in the loop, is now transformed into the IS. Okay, so that we have IS inside the loop. Okay, so we can now apply the KVL according to the equation here, where we have a negative 3 over S plus 2S IS, voltage drop across this component, minus Li0 negative, which is the voltage source here, okay, and plus 4Is, which is the voltage drop across the resistor, and equals to 0. So this is the KVL equation. So we need to factor out the Is. So afterwards, we are going to have the Is in this particular form. So as what we have learned before, we need to write this into a partial fraction, which is A over S plus B over 2S plus 4. Yeah, so we need to write in this particular form. So by using partial fraction method, we have then obtained that the IS basically should be equal to 0.75 over S plus 8.5 over 2S plus 4. Okay, so you can work out for the A and B value. You are supposed to get this 0.75 for the A and 8.5 for the B. Okay, so we are yet to obtain the answer, because your answer that you have obtained here is in the S domain. So you need to do the inverse of Laplace transform to find the value of current in time domain, the IT. So this will be based on the properties of Laplace transform that we have learned yesterday. Okay, so 0.75 over s is 0.75 ut, and also 8.5 over 2s plus probably 4.25 exponential negative 2t of ut. Okay, so this is the way how we use Laplace transform in solving the circuits analysis problem, in which this method is very much easier, yeah, as compared to the solutions in a conventional time domain technique. Yeah. Okay. Any questions so far on these examples? On these first examples here? No. Okay. If there's no questions, let us proceed with the second example here. Okay, so we are having this circuits where we have two resistors. We have the we have the R of 1 ohm, we have the R of 2 ohm, and we have inductor L and capacitor C of 1 farad. Okay, it's given that, so you have 3 volt here, yeah, 3 volt of voltage. It's given that the switch is connected to A at t equals to 0. Okay, so which means that initially the switch is at B. So when t equals to 0, the switch is now connected to A. So at t equal to 0 onwards, we're going to have this component which consists of 2 resistors and 1 capacitor. So we can ignore this inductor, yeah, for the case of t bigger than 0. Okay, so inductor can be ignored, yeah. So we assume that the initial voltage source V0 negative equals to 0. So this initial voltage is related to the capacitor's 0 voltage, yeah. So capacitor's initial voltage VC0 negative. Okay, always be reminded that for the inductor L, we are dealing with the initial current source. So initial current source, correct? Yeah. Whereas for the capacitor, we are dealing with the initial voltage source. Okay. Okay. So for the capacitor, the initial voltage source is given to be 0. Yeah. All right. So as what we have learned previously from the slides, yeah, for the capacitor of C in time domain, the transformation into the S domain will be 1 over SC, yeah, 1 over SC, and in series with the voltage source, yeah, in series with the voltage source, and because the voltage source here is 0, so there should be no voltage source involved in your components of the capacitor. Okay. Yeah, so resistor is remain to be 1 ohm and 2 ohm should be there, no changes for the resistance value, and the voltage source of 3 volt is now returned to be 3 over S. So this is a transformation of your circuit from this time domain into the S domain. Yeah, so remember that there should be no voltage source in series with the capacitor's impedance, because your voltage source value, initial voltage source value, is given to be 0. Yeah, so that's why there is no voltage source in series with these capacitors impedance. Yeah. All right. Remember what you need to obtain here. We need to find the VT. Yeah. VT is what? VT is the voltage drop across the capacitor. Yeah, that should be the VT that need to be obtained. So it means that to find the VT, you need to find the current. Yeah, you need to find the current IT that flowing through the circuit. So once you know the current, you can find the voltage drop across the capacitor. So you need to find the IT. Yeah. Okay, so that's the idea. So based on that, you can say that you want to find the current IT, so we transform it into IS. Okay, so that should be the circuit that has been transformed into the S domain. Okay, so we're going to have negative 3 over S. Okay, IS here is the current, voltage drop across 1 ohm. 2IS is the voltage drop across 2 ohm. And 1 over SIS is the voltage drop across the capacitor. Okay, so afterwards, we want to find the IS, so we can write the IS in terms of this equation. So by right, you can solve it. Yeah, we can solve it. Sorry, yeah, we can solve it by this. So the IS is the uh, current. Yeah, this is the current that flowing in your loop here. And knowing that you want to find the voltage across the capacitor, so the VCS, or simply we just write as a VS, shall be equals to the current, which is 3 over 3S plus 1, multiply with this impedance of the capacitor, which is 1 over S. Yeah. So 1 over S is the impedance, and 3 over 3S plus 1 is the current. Yeah. So that is Vs equals to Is multiply with 1 over S. Yeah. 1 over SC. Yeah. Because C is 1 farad. Okay. C is 1 farad. So we just have 1 over S. Okay, so again, we need to use partial fraction. Okay, partial fraction for that term. So we're going to have 3 over s minus 9 over 3s plus 1. Okay, so using the properties that we have learned yesterday, we can then write the Vt, yeah, in time domain should be equals to 3 of ut minus 3 exponential negative 1 over 3t of ut. Okay, so that should be the voltage across the capacitor in time domain. All right. Any questions so far on this example? So we did the examples that involve the R, the L, and also the capacitance C so far. Yeah. All right. So this is the second method in which if you want to solve the circuit using the node analysis, in which the current method, the method that need to be used here is the Kirchhoff current law, the KCL. Okay, right. So this is the step that need to be taken. Replace resistor with R, yeah, in S domain. For the inductor, we need to transform into the impedance SL, which is in parallel with the current source, yeah, as what we have learned in the previous slide. And also for the capacitor, need to write it into or transform into the impedance of 1 over SC, and in parallel with the current source also, as what we have learned before, yeah. Okay, so again, the current source need to be transformed into the S domain. Okay, so as usual, sketch the transform diagram, means this is the S domain, yeah, the S domain. So this is what we have done before. And finally, the third step is to use the KCL at respective node and to solve for the given parameters. For the required parameters, yeah. Okay, so I think the method should be similar as what we have learned before in KVL, but just to be, you need to take care of this transformation, yeah, the current source for the inductors and the current source for the capacitor, yeah. So this is based on these slides. Okay, slide number 6 for the capacitor. This is the one. Okay, this is the one, the transformation into current source. Okay, and also slide number 4 for the inductors. Okay, this is the one. Okay, then let's have a look at this example to test our understanding on this node analysis. Okay, so we are given two nodes here. Yeah, we are given two nodes, and for this particular nodes, we have a capacitor C1, we have capacitor of C2. The voltage is V1 across the C1 capacitors of 1 farad. The V2 is the voltage source, the voltage drop across the C2 capacitor of 0.5 farad. We have a resistor of R 1 ohm, and there should be a switch over there. Okay, the question, the information given is that this S switch S is closed for t bigger than 0. Okay, t bigger than 0, switch is closed. Assume that the voltage source VC1 0 negative is 2 volt and VC2 0 negative is 1 volt. Okay, so it means that initial voltage for the C1 capacitor C1 is 0. 0. It is 2 volt initial voltage. Initial voltage for the capacitor is 1 volt. Okay. Sorry, I apologize. I need to take a phone call, just for a while. Thank you. Sorry for the interruption. There's a call from my colleague. Okay, I received a question from Ling Jing Kai. Can we ignore the UT? Okay, Jing Kai, which UT that you mean? Which UT that you mean? Is it a voltage or what then? Sorry, Jing Kai, which UT that you? Is it this UT over here or what?
I think it's the next slide.
The next slide, which one then? Is it this one?
I mean, that 0.75.
0.75, let me see, 0.75, where is it, 0.75? Oh, this one, is it?
I mean, yeah.
Yeah, okay, I think we need to write it as 0.75, I mean, yeah, should be okay then, because it's a current, right? So we can just write 0.75, that should be good enough, lah. Yeah, so it's understood to be the value which is bigger than 0. Oh, should be okay then, no problem. Yeah, okay, very good. Yeah. Okay, so let us proceed with this solution for this example for the analysis. All right, so this will be the transformation for the circuit. Okay, we have 1 farad of capacitor, so it should be 1 over SC, yeah? Sorry, it should be 1 over SC, yeah? All right, so we have, this is 1 over SC, so 1 over SC, and remember that we have the voltage here, so what should be the voltage current equation? So for the capacitor, we have to go back. So this is CV zero negative, yeah? So that should be the equation for the current source, yeah? CVC zero negative, right? So this is CVC zero negative. Again, this is CVC zero negative. So we are given that for the case of capacitor C1, okay, it is 2 volt, right? 2 volt. And for this capacitor, the value of capacitor is 1 farad. So 1 times 2 should be 2 ampere. Okay. And for this particular case, for capacitor of C2 is 0.5 farad. And the voltage, initial voltage is 1 volt. So the current is 0.5 ampere. Okay. So that's why we have 0.5 and 2 ampere for this current source. Yeah. Right. So this is what we're going to have for the circuit's transformation from time domain to a frequency domain. Yeah. So hopefully you have understand now how to transform from the time domain circuit into the S domain circuits. Yeah. Okay. So you need to find the question is to find the V2T. Yeah. V2T is the voltage here, which is the voltage across the capacitor C2. Right. So this is the voltage need to be obtained. Okay, need to be obtained is a V2. So we can use the KCL now, Kirchhoff current law. So we are having two nodes A and nodes B. So at node A, this is the equation of KCL. All right, so 2 ampere minus V1 over 1 over S, which is the current. Yeah, and then we have, so this is the current and should be this direction then. Okay, so V1 minus V2. V1 minus V2 divided by R equals to 0. Right, and okay, that should be the case here in this direction. And then we have this and node B, sorry, I think I have a mistake now, sorry. Yeah, right, sorry for that. Okay, and then we have and node B, yes, with the equation for the KCL 0.5 current, negative V2 over 2S plus V1 minus V2 over R equal to 0. Yeah. Right, so from this equation number 1, this is the equation that relates the V1 and the V2, yeah, V1 and V2, the voltage across the capacitors, yeah, and we need to substitute this relationship of V1 and V2 into this equation, okay, so we can then obtain only the V2 values, yeah. So we have then substituted the V1 here in these components, yeah, equation number 2. So the V1 is now returned in terms of V2. So after all, we can find the V2 itself, yeah. So the V2 is 5 over 3S minus 2 over 3S plus 3. which can be obtained by using the partial fractions. And afterwards, we can do the inverse of Laplace transform, yeah, in which from what we have learned yesterday, it should give us 5 over 3 ut, yeah, minus 2 over 3 e exponential negative 3t of ut in time domain, yeah. So that should be your v2t. So basically, there's nothing much about, there's nothing much to be worried about this, this topic, because I believe that you have a very good understanding on the circuit analysis. Okay, so fundamental is there. So the important things here is only on the transformation or the passive component, the R, L, and C, from time domain to its respective S domain components. Yeah, so that's all. Okay, so let's have a look at this example number 1. Okay, we are having these circuits consists of one voltage source of delta T. Okay, so we have 2 Henry of inductor, we have 0.25 farad of a capacitor, and we have 6 ohm of resistors. Yeah, right. So that should be the components of your circuit. So number 1, the question is we need to transform the circuit to the S domain and need to write or draw the circuit. So this should be a transformation of the circuit, yeah, from time to the S domain. Right, so in this particular case, we don't have any information about the initial voltage, right? Because there's no such switch given. Yeah, there's no such switch given on the circuit's component. So by right from this circuit, we cannot deduce any information about the initial voltage and initial current. So as such, what we can do is that we can assume that initial voltage and initial current, both of them are 0. Okay, so that is our assumption. Yeah, initial current for the inductor and initial voltage for the capacitor, both of them are equal to 0. Yeah, so that should be our assumption. Okay, so for this, we can simply proceed with the circuit transformation to the S domain, right? So delta t, which is an impulse, shall be now returned. Okay, so now I'm going to do the transformation here. Okay, so for for the delta t, the transformation for delta t will be simply 1. Okay, you can refer to the notes. Yeah, impulse function delta t, when we transform into the S domain, it will result of on 1. Yeah, that should be the value. Then for this 2 Henry inductor, it should be 2s. Yeah, because inductor is SL in terms of in the S domain, the inductor is returned to be SL, the impedance. For the capacitor, okay, for the capacitor, we are having 1 over SC, okay, 1 over SC, right? And since C equals to 0.25, so that should be equals to 4 divided by S for the impedance of the capacitor. For the resistor, will remain as 6 ohm, yeah, and that should be the circuits that has been transformed into the S domain. Okay, simply we have this as the circuit transformation because we have assumed that the initial current of the inductor and initial voltage of the capacitor are 0. Okay, okay, so that's answer the questions number 1. Okay, right. So next is need to write the equations of the voltage in the S domain. Yeah, voltage in the S domain. Okay, the voltage is the Vs here. Basically, if you base on that, the Vs is the transformation of the Vt. Okay, Laplace will give us the Vs, whereas for the It will give us the Is. So we need to write equations of Vs, the value of Vs in terms of the Is, right? So we need to write we need to use the KVL to find the Is. Okay. So from these circuits, we can write the KVL. Using the KVL, we're going to have 1. Okay, that should be the arrows, yeah, the current, the Is. So we're going to have 1 equals to 2s, okay, plus 4 over s, plus 6 multiply with the Is. Okay, that's all. Yeah, so that should be the equation, yeah. So from here, we can have that the IS, okay, shall be equals to, okay, we can have S divided by 2S squared plus 6S plus 4. Okay, so we can have it as the um, partial fraction, I believe. Yeah, so that should be written as S divided by, okay, 2S plus 2 and S plus 2. Yeah, okay, so that should be the IS now, yeah, which is the current across, I mean, current in the loop. So the VS shall be written as R multiplied with IS. Okay, VS is this voltage across the resistor. So R is 6 ohms. So we're going to have 6 S divided by S plus 2 and 2S plus 2. Okay, so that should be your VS. Yeah? The voltage across the resistor in the S domain. Okay then? Hopefully it's okay. Yeah? Right. Also, we need to find the number 3 is to find the IT. Okay, I think this is done. Yeah, that is done. Number 3 is to find the IT when the switch is closed at time t. So there's no switch basically. There's no switch. So I'm not sure where the switch come from. Sorry for that. Yeah. Okay. And again, it's assuming that the I0 and V0 is 0. So this is similar to our assumption just now. Okay. So to find the IT, simply we need to use this equation that we have obtained before. Sorry, this equation here. Okay, this equation. So IS to be equals to 2 over, sorry, S, I apologize, yeah, S over 2S plus 2, S plus 2, so we need to use a partial fraction, A over 2S plus 2 plus B over 2S, sorry, B over S. S plus 2, yeah. Okay, so if we base on this, basically, yeah, you can work out for the partial fraction. Can you do this on your own? Is it okay for me to skip this part? Or you still need me to solve it for you? No response?
It's okay, doctor.
Oh, okay, yeah. So you can solve it on your own, yeah. Okay, thank you very much. It's a relief for me then, yeah. So you have to be based on the partial fraction. Thank you. So I think nothing much to be worried here, yeah. So it's very simple, straightforward only. So when you have it, once you have the value, once you have obtained the A and B value, so please do the inverse of Laplace transform, and you can find the IT straight away, yeah, using the properties that we have learned yesterday. Okay, so that's all for this example. It's very straightforward. Okay, any questions up to now on these topics? I mean, on this example so far? Is there any questions so far? No? Okay, if there's no question, I think we can proceed with the next example. Okay, this is the example that we're going to learn. All right. So we are given a rectangular pulse of VRT, which is applied to the RC circuit as shown in figure question 3C. Okay, so the VR is given to be a rectangular pulse from 0 to 2 duration of time, and the amplitude is 1 applied to this RC circuit are of 10 power of 6 ohm, and capacitance C is 1 microfarad. Okay, right, so we need to sketch the Laplace transform equivalent circuit of figure question 3C. Number 2, using Laplace transform, determine the voltage response of the V naught T. Okay, so for this particular example, we need to find, I mean, we need to know what should be the value of initial voltage for the capacitor, yeah? Because we have a capacitor here, 1 microfarad, okay, sorry, 1 microfarad, but because we don't have any informations given, yeah, we don't have any switch, yeah, we don't have any information on the initial voltage. So we assume that the initial voltage for the capacitor in this particular case, the VC zero negative is equal to 0 again. Okay, so that's our assumption. Yeah. Okay, so from here we can straight away proceed with the circuit transformation. Okay, so we know that uh, for this particular circuit, the VRT is given to be a pulse from 0 to 2 with the amplitude of 1. So we need to write this in terms, in a form that can be transformed, yeah, by Laplace transformation. Okay, so the best symbol or the best signal that shall be used here is step function. Okay, in which I can write that my VRT here shall be equals to ut minus ut minus 2. Okay, so that should be the easiest, I mean the simplest representation of the VRT, in which this can be simply transformed into the S domain, yeah, using the properties that we have learned yesterday. Yeah. Okay, so now we can transform into the S domain, right? So your component, your voltage source, okay, shall be transformed. Yeah, it shall be transformed, in which ut minus 2, when we transform it, you're going to have 1 over s minus 1 over s exponential negative 2 of s. Okay, that is the transformation for this VRT. Okay, we have seen this, we have learned this yesterday. Okay, ut, the transformation is 1 over s, ut minus 2, a transformation is 1 over s exponential negative 2 of s. Yeah, that's why we have this as a transformation for the voltage source of VRT. Okay, for your resistor, it remains as 10 power of 6. Nothing much. There's no difference for the resistor. For the capacitor, we have 1 microfarad or 10 power negative 6 farad. Okay, and we know that for the capacitor, we need to transform it into the impedance of 1 over SC. So as such, the capacitor will be now returned to be 10 power of 6 divided by S. Okay, and that should be the circuit transformation from a time domain to a frequency domain. Okay, so that answers question number 1, which is to transform or to sketch the Laplace transform equivalent circuit of this figure. Yeah, so that should be the answer. Okay, number 2, by using Laplace transform, determine the voltage response of the V0 T, which is the voltage across the capacitor. Okay, so for this, what we need to do is that we need to find the current. Yeah, find the current. So let us say that this is the current flowing in the loop. So we write this as the IS. So in order for us to find the V0 T, you need to first obtain the current. Yeah, and once you obtain the current, you can find the voltage drop across the capacitor in the S domain. Then only you can do the inverse of Laplace to find the V0 T. Yeah, so that's the idea. Okay, let us proceed with this IS. So from that, for KVL, yeah, using the KVL, we can write for this particular circuit that the voltage source 1 over S minus 1 over S exponential negative 2S. Okay, and that should be equals to IS multiply with 10 power of 6 plus 10 power of 6 divided by S. Okay. Right, and then we can write the IS. We can have the IS term. So IS, okay, shall be equals to S divided by 10 power of 6S plus 10 power of 6. Okay, and multiply with, sorry, it's 6 over here, yeah? Multiply with 1 over S minus 1 over S exponential negative 2S. Okay. Hopefully it's clear, yeah? Right. So that should be your IS. Okay, so from here we can find the V naught S, which is equals to 10 power of 6 divided by S multiplied with the IS. Okay, and it should be equals to 10 power of 6, yeah, over S multiply with the IS that we have obtained here, which is S over 10 power of 6S plus 10 power of 6. Okay. and multiply with 1 over s minus 1 over s exponential negative to s. Okay, so this s and this s can be cancelled out. This 10 power of 6 and this can be cancelled out. So we're going to have what? We're going to have 1 over s plus 1 multiply with 1 over s minus 1 over s exponential negative 2 of s. Okay then? Okay. Is there any questions so far on these issues? No, yeah? So I think we have done with this. So once you have the V naught S here, okay, you can now proceed with with finding the V naught T using the inverse of Laplace transform. Is it okay? Okay, so I left this. Yes.
Can we use voltage division to find the voltage in capacitor in S domain?
Come again, I cannot hear you clearly.
Can we use voltage division to find the voltage in the capacitor in S domain?
Voltage division to find the voltage
In the capacitor.
on the capacitor.
Yes.
Okay. I think the method is the same. Method is the same. Like what we have here. The same method. Okay.
Okay.
All right. So I think so we have done with this example. So I'm going to stop the lectures today at this point. So we are going to continue our lectures next week on Sunday. We're going to have more examples on a Laplace transform circuits analysis. Okay, so this will be the last topic for lecture chapter 4. Okay, and also on Sunday, after finishing this topic of circuit analysis, we're going to have a tutorial session on chapter 4. And please be reminded that we are going to have a third quiz on Monday. Yeah, third quiz on Monday. The topics for the quiz on Monday will be on Fourier transform. Yeah, the topics for the quiz on Monday will be on Fourier transform. Okay, so please be reminded on that schedule for next week's class. Yeah, so again, next week's on Sunday, we're going to proceed with this Laplace transform circuit analysis. We're going to end it next week on Sunday. Afterwards, we're going to have a tutorial for chapter 4. And on Monday, we're going to have a quiz on Fourier transform. Okay, so that will be a schedule for next week. So with that, I end the session for today's class. Any more questions before we end the class today? Any questions? No questions. Okay, thank you very much. Yeah, thank you for your attendance. Yeah, take care. See you again next week. Yeah. Okay, bye-bye. Thank you very much.
Thank you, Doctor.
Thank you very much.